Hello everybody. In today's lecture, we're going to go ahead and start talking about water and the special properties that water has. Some of the goals and objectives of today's lecture is going to be talking about the properties of water that are critical to life. We're going to be able to describe water as the universal solvent. We're going to talk about water's cohesive and its adhesive properties. We're going to discuss acids, bases, and buffers in homeostasis. Explain the pH table, and we're also going to be able to make a molar solution by the end of this lecture. So why should we study water? The most important reason why we should study water is because water is actually the compound that supports all of life. As you know, you and I are actually made up of around 70% water molecules. Okay, it makes life possible on Earth. Organisms are made and live predominantly off of water alone. Water can exist as a solid, a liquid, and a gas. And water has a very, very, very rare property in its solid state as it floats on its liquid state. So in other words, when water is frozen as ice, something special about it that allows it to actually float compared to its liquid state, such as regular water molecules in its liquid form. So what is it exactly that's allowing water to do these crazy different features? Okay, one thing you want to recognize is that water are actually known to have polar, they're known as polar molecules. Okay, so water forms hydrogen bonds with each other. So what do we mean by a polar? So each one of these individual molecules of water, this is H right here, H2, so that's why there's two hydrogens attached to this oxygen molecule. So the hydrogens are actually slightly positively charged and the oxygen is slightly negatively charged. What that means, polar means, is that there's an unequal sharing of electrons between these two atoms. So in other words, the electrons are going to be circling around the oxygen and spending more time around the oxygen than around the hydrogens themselves. Okay, so that's what polar means, unequally sharing of electrons around a molecule. But like we were talking about water in this instance, water, okay, here's one water molecule, here's another water molecule. Water is actually going to form hydrogen bonds within each other. So here's the negative oxygen of one water molecule, and it's actually attracted to the positive end of this hydrogen on another water molecule. So in between water molecules themselves, they actually form these hydrogen bonds. Okay. And just to mention, hydrogen bonds last a few trillionths of a second. So as we actually heat water up, these bonds are constantly being made and broken over and over and over, okay? Very, very short time period that they actually last. So polar or nonpolar depends on the bond type and their shape. So as we mentioned, here's a water molecule, and it's considered to be polar, which means it does not equally share the electrons around both atoms. So let's say here's the electron's going to take a lot more longer to go around this oxygen, and it's going to go very quickly around the hydrogen, around oxygen a lot longer, very quickly around hydrogen again. Okay, so polar is what water is considered. But we also have nonpolar, which means they're gonna be an equal sharing of electrons. For example, this right here, this carbon dioxide, CO2, the electrons are going to equally share around each of these atoms as they're circling around that outer shell of its atom, okay? Equal sharing of electrons. Some examples of some nonpolar liquids might be oil or alcohol. So these are going to be some important properties of water to know. Number one, we're going to mention its cohesive nature, its also ability to moderate temperatures, its ability to expand when it's frozen, and also its versatility as the universal solvent. Down below, we'll talk about the other things when we get to them, but it's more of a overall picture. The top four items are actually what we're going to be talking about when we're talking about the properties of water. Down here is when we're getting into the acid and bases and the molarity of things. So talking about water still. So cohesion, what cohesion actually is water sticking to water molecules. So like molecules sticking to like molecules, okay? This is actually what gives this little insect right here the ability to actually just stand on the water like it's doing right here without ever breaking that water tension right here on top. The way it's able to do this is because those hydrogen bonds we talked about earlier, remember, they want to actually hold on to one another. They're attracted to one another. So they're actually holding on to each other, kind of like a little piece of plastic across the surface of the lake. But in this case, it's just the hydrogen bonds that are not broken because this insect is not heavy enough to break those bonds. So that's why the water molecules are not broken, and he can actually sit on top of the water. And this is what's called surface tension. You'll also see surface tension, like, for example, if you actually fill up a glass of water and then continue with a little dropper to keep filling it on top, above its top rim, the water molecules will start actually making this concave, almost like a contact lens shape over the cup itself, because it's also, once again, due to surface tension, those water molecules and the hydrogen bonds trying to stick to each other. Now, under that umbrella, when we're talking about cohesion, is also what is known as adhesion. Adhesion is water molecules sticking to unlike molecules. So imagine the best example I can think of is, let's say you have that cup of water, it's full of water, and you dump it all out. Those tiny little water droplets that are still stuck to the side of the glass, that is what's known as adhesion, okay? Water molecules sticking to its unlike molecule. Now, I know we just talked about cohesion, which is, remember, cohesion is water sticking to water molecules. So once again, that allows for the surface tension, okay? But adhesion, like we just said, water molecules sticking to other surfaces. Well, one good example of this would be actually capillary action. So what that actually means, or a good way of thinking about this, is like when you go to the doctor, you know how sometimes they'll go ahead and prick your finger for some blood? Well, they actually put a tiny, tiny little tube there to actually suction up the blood so they can go ahead and test it. So during capillary action, it pretty much means the thinner the tube, the higher the water will travel. So that's why they don't have this big, thick tube to get your blood out. They want a very, very thin one because the actual water that's retained in your blood wants to grab on to the molecules around it. Another good example would be what's known as turgor pressure. This is what happens in plants and trees. Okay, so turgor pressure is the way how we would refer to this if we were talking about plants. So the water actually gets sucked up and absorbed by the root hairs of these huge, huge trees, and then through adhesion, which is basically water sticking to unlike molecules, they actually kind of find their way all the way to the very, very tops of trees. So due to adhesion and cohesion, remember, water sticking to water, they kind of like form this little ant-like structure going all the way up on the inside of the xylem of the trees in order to give these very, very top leaves the water that they need to go ahead and continue growing. The second property of water we'll be discussing today is the moderation of temperature. During the summer months, water is actually able to absorb heat. Okay, that heat that water absorbs during the summertime, what it does is it absorbs it and it maintains it, and then it releases it in the winter. So water actually has a very, very high specific heat or high heat capacity, meaning it doesn't want to change temperature very much, which is good for us because, like I said before, we actually are made of about 70% water. And so obviously our bodies have to remain at homeostasis. So it has to have a specific temperature that we're okay at, or that our bodies function the best at. So in other words, for water liking to resist the change of heat, that's good for us, okay? Just like it's good for us in order for it to actually help us heat the earth. So water actually is also responsible for evaporative cooling. So water evaporates if you're boiling water, let's say, for example, or even when you start sweating. What that sweat is actually doing is cooling your body down. And once again, it does the same exact thing for the planet Earth. The third property of water we'll be talking about today is going to be how it actually is able to insulate bodies of water by floating ice. So what's actually happened is when water is frozen, it is actually less dense at this solid state because the hydrogen bonds become a lot more stable. Remember, those hydrogen bonds are constantly being broken and then reattaching to another bond, oxygen and hydrogen, constantly. But when temperatures are at freezing points, which is 0 degrees Celsius for water, then what it does is water actually starts expanding and those hydrogen bonds are actually held in place. Well, like I said, when they are held in place, they're a lot less densely packed. So you see how there's a lot fewer water molecules here because it's less dense than the liquid form of water right here. Well, anything less dense than the liquid form of water will float, which is why ice is able to float on the top of liquid water. But let's say during the winter months, by the lakes and some sort of ponds able to freeze over that one top layer, it actually creates an insulation down below for any kind of organisms that are going to survive the winter months. The fourth property of water we'll be talking about today is water as an actual solvent. It is known to be the universal solvent. So what that means is let's go ahead and discuss solution, solute, and solvents. So a solute plus a solvent equals a solution. So a solute, for example, would be, let's say you have sugar. So let's say you put sugar as your solute and then you combine it with your solvent, let's say water. So you combine those two together and you make sugar water once all the sugars dissolved nicely in a nice homogeneous mixture. But one key thing to know here once again is water is the universal solvent. Okay. Two terms really good for you to know would be hydrophilic and hydrophobic. Hydrophilic means water loving. Hydrophobic, anything with a phobia, it means water fearing. So let's go ahead and jump into the moles now. We measure the number of molecules in units called moles. The number of molecules in a mole is equal to Avogadro's number. So what that means is mole is 1 unit of a compound or a molecule. For example, see right here. Let's say I have O2, oxygen, right? Oxygen, this O2, which is what we breathe, there are 2 oxygen molecules here, but this is still equal to 1 mole. Because remember, a mole is 1 unit of a compound or a molecule. So this is a compound right here, so 1 mole. Another example. If we had the same instance, but this time we have 2 O2, this would actually be equal to 2 moles because of the fact that this was 1 molecule, 1 mole. But if we add the 2 in front of here, that means there's 2 O2s, that means 2 moles here. Another example would be, let's look at water, H2O. There's only 1 compound here, so that means there's only 1 mole here. 1 of any substance. So let's say, so the number of molecules in a mole is 6.02 times 10 to the 23rd. That is what's known as Avogadro's number. So if you have a question that asks you how many atoms or molecules are in 1 mole of a substance, the answer is always going to be 6.02 times 10 to the 23rd. And the mole is equal to the molecular weight of a substance in grams. Okay, and we'll look at that in just a second. So 1 mole of a substance has the same number of molecules as 1 mole of another substance, even though they have different molecular weights. Okay, so you should know how to actually find out the molecular weight of a compound. But let's just say, for example, let's say you're trying to figure out H2O. And somebody asks you, what is the molecular weight of H2O? So what you have to do here is first, and you have to pull out your periodic table for this part, okay? And do not round on the periodic table. I would just go ahead, like let's say, let me see, for example, if we're looking at hydrogen. Hydrogen is usually equal to 1 gram on the periodic table. So you would do hydrogen there's 2 atoms of hydrogen here, so it'd be 2 times, and if you look at the periodic table, it is actually 1 gram, so that'd be your 2. Then oxygen, there's only 1 atom of oxygen, so oxygen would be your, and there's only 1 atom, and here's your grams, 16 grams, and that'd be your 16 right here. Then you add these 2 up together, 16 plus 2, that's going to give me 18 grams. That is the molecular weight of H2O. Okay, remember, 1 mole is equal to the molecular weight of a substance in grams. So 18 grams of H2O is equal to 1 mole of H2O. So let's get into molarity now. So the concentration of a material in a solution is known as molarity. The number of moles of solute per liter of solution. So let's look at this example. How would we measure 1 mole of sucrose or of ethyl alcohol? So we're going to discuss now pretty much how to make a molar solution. But first, let's backtrack real quick. Let's look at this question real quick. Remember what I just told you about atoms and molecules. So how many molecules of glucose, that's what C6H12O6 stands for. So how many molecules of glucose with a molecular mass of 180 daltons would be present in 1 mole of glucose? So if you see questions once again saying molecules or atoms, then that is the answer, the 6.02 times 10 to the 23rd. Remember that, okay? But if it's asking for your molecular weight of something, then that would not be the answer. But let's say, for example, you get asked to make 1 molar solution of sodium chloride. So what you're going to have to do first, and remember, just a little keynote, is daltons is equal to grams. So anything given in daltons, you can also say it's in grams. Okay, so if I say sodium is equal to 23 daltons, you can also say sodium is equal to 23 grams, or chlorine is equal to 35.5 grams. Okay, so this is how you make a 1 molar solution of sodium chloride. First things first, you have to find molecular weight equal to 1 mole. So you already have molecular weights right here, but they're given you here. But let's say you had your periodic table out, you'd be able to find these as well. So in sodium chloride, there's only 1 atom of sodium, 1 atom of chloride. So remember, we're going to add those together because there's only 1 atom of sodium, so that'd be 1 times 23 grams. And then we're going to also have 1 chlorine atom, and that's going to be times 35.5 grams. All right, multiply those out. Obviously 23 plus grams of sodium, and then plus 35.5 grams of chloride. That's going to equal to 58.5 grams of sodium chloride. That right here, what we just figured out right here first, is going to be the molecular weight of sodium chloride compound. Okay, that's the molecular weight. So next what we're going to do, and this is how you make a 1 molar solution, which is usually a standard solution that you should always know how to make. Okay, first you're going to get a flask, a 1 liter flask. Okay, after you get the flask, you're going to fill, let's say this is a 1 liter flask, huge 1 liter flask. Okay, and this is the mark for 1 liter. And remember, 1 liter is also equal to 1,000 milliliters. Unless told otherwise, this is usually the standard, like I said, you will make when you're talking about molarity. Okay, so first things first, you're going to go ahead and fill the 1 liter your flask with halfway full of water. So you're just going to eyeball it, fill it to about 500 milliliters right here, full of water. After you fill it full of the 500 milliliters of water, then you're going to add your 58.5 grams of sodium chloride to your mixture. Then all you're going to do now is eyeball it, and looking at it from an eye level, you're going to go ahead and fill the rest of the flask up until the 1 liter fill mark. So once again, fill it up halfway with water, add your substance. After you add your substance, fill it up into the 1 liter mark. Now you have completely made a 1 molar solution of sodium chloride. Once again, reminder, Daltons is also equal to grams. So go ahead and try to figure this out yourself. How many grams of acetic acid would make 10 liters of a 0.1 molar aqueous solution of acetic acid? Alright, so now one thing to point out is that water can dissociate. Okay, why is that important to know? Because water itself, H2O, can dissociate into regular hydrogen ions by themselves, just regular hydrogen ion by itself, just kind of hanging out. And the other two things that would be left would be a hydroxide ion, which is this guy right here. This is important when it comes to acids and bases because the greater the number of hydrogen ions in a concentration of a solution means that it is acidic. If there is a very low number of hydrogen ion concentration of a solution, then that means it is basic. Okay, so with that being said, also, these kind of go hand in hand. If there's a high number of hydrogen ions in the concentration, then that means that the hydroxide number must be very low. With this one, if there's a very low number of hydrogen ion concentrations of a solution, then that means that the hydroxide ions must be very high. Like I said, these guys go hand in hand together. Okay. And pH, what that is actually standing for is the probability or the possibility of free hydrogen ions available on a scale level. So let's go ahead and look at the scale next. Right here is a scale. Let me go and erase that guy real quick, sorry. All right. So right here is the pH scale. A lot of you have seen this one before. So looking at this, let's go ahead and look at it like in the sense of from a 0 to 7 pH and then 7 to 14. So the pH scale, as you can see, runs from a 0 all the way to 14 value. Okay. Anything water, let me just put that out. Water is neutral. Water is neutral at around 7 pH. Anything less than 7 is considered to be acidic. So it's going to be a very, very high hydrogen ion concentration. Remember, acids, very, very high hydrogen ion concentration. If anything is greater than 7, then you're looking at a basic solution, which means we're going to have very high hydroxide ions available in this concentration and very low hydrogen ions available here. So one easy way to remember, like let's say acidic, which is anything less than 7, would be I like to think of it as like Los Angeles, LA. The low pH means acidic. Lower is acidic. Okay. So if you get asked a question like how much more acidic is digestive juices than tomato juice, well, how would you figure this out? Most people would answer the question with it is 2 times less or more acidic than tomato juice. That is actually incorrect because every single one of these little steps is multiplied by 10. So from 2 to 3 is times 10. From 3 to 4 is times 10. So right from right here to here is times 10. Here to here times 10. So since we have 10 from 2 to 3, we also have 10 times from 3 to 4. We multiply those two together and it is actually equal to 100 times. So the actual correct answer would be that digestive juices at pH of 2 is 100 times more acidic than tomato juice at pH of 4. pH of blood is close to 7.4, so it's actually our blood levels are basically slightly basic. And a person cannot survive for more than a few minutes if the pH of blood drops to 7 or rises to 7.8. Because we have a very short range on what we could survive at, we actually have buffers. Buffers resist changes in the pH of a solution when hydrogen ions or hydroxide ions are added to a solution. Buffers are what pretty much allow us to survive if we drink anything acidic like orange juice, okay, or if we eat something basic like steak. So here's a question to think about. The following are pH values. So you have cola 2, orange 3, beer 4, coffee 5, and human blood 7.4. Which of these liquids has the highest molar concentration of hydroxide? So if you know it has a high molar concentration of hydroxide, remember, high hydroxide means it's actually going to be more basic. So remember, La, so the lower pH, it means it's acidic. So the opposite, we want a higher one. So the highest out of all of these would be human blood, since it's asking for the highest concentration of hydroxide. If the pH of a solution is increased from pH of 8 to pH of 9, what does that mean? Well, remember 8 to 9 is just one level, so it is only 10 times different. So the answer here will be the concentration of hydroxide is 10 times greater than what it is at pH of 8. Buffers, like I said, they just allow for minimum changes in concentration of hydroxide and hydrogen ions in a solution. And here's a good way to help practice for the exam as well. So, how many grams of a molecule in this figure would be required to make a 1 molar solution of the molecule? So, it is asking for weight. So, first things first, you would have to figure out the molecular weight of this molecule. Because remember, one compound of this molecule is equal to 1 mole. So, there's 2 carbon, and then 2 times what's the molecular weight of carbon on your periodic table? 12 grams. Okay, that's for carbon. Now, oxygen, there's 2 atoms of oxygen here, and the molecular weight of oxygen on your periodic table is 16. Okay. And last but not least, we have 4 atoms of hydrogen. So 4 times the molecular weight of hydrogen is 1 gram, which is also in your periodic table. So 12 times 2, 24 grams. Oops, 24. 16 times 2 equals 32 grams. And then we have the last one, 4 times 1, which is 4 grams. Add all these up. And that weight you get right here, which I'll go ahead and not tell you. Okay, let's see what you come up with. Give you a second. Alright, should be 60 grams. 60 grams would be how much of the actual whole compound you need to make 1 molar solution. So remember, how would you make a 1 molar solution again? First things first, fill it up halfway with water. Then add your substance to it. After the substance has been added, then you're going to add water using eye level view till it reaches the 1 liter fill mark line. And just a recap of what we went over today. We went over the properties of water that are critical to life. We described water as the universal solvent. We described water's cohesive and adhesive properties. We talked about acids, bases, and buffers to maintain us in homeostasis. We also explained the periodic table as well as the pH table and the using of it to figure out molecular weights of compounds. And you should be able to go ahead and now know how to make a 1 molar solution of substances.